We've looked at how to integrate over lines, surfaces in the plane, as well as regions in 3-space. But now let's look at integration over curved objects. What I mean by that is if we look at a one-dimensional integral, the integral from a to b of f of x dx. Now you can think of this like the area under the curve, integrating from a to b. And now our curve can have some, well, curve to it. But the region of integration, the interval from a to b, is flat. So when I say integrate over something that's not flat anymore, I mean this region of integration, this interval from a to b. The first type of this curved integral we're going to look at is called a line integral. And there are actually two types of line integral. First is the scalar line integral. And the next is called the vector line integral, the field line integral. And the scalar line integral is defined in the following way. We're going to integrate over some curve c of f of x, y, z. And then usually what gets tacked on at the end here is this ds. So one application, before we define what this is, one application of this is if we think of this like the mass, or not the mass, the density function. Then you can think of this quantity as, say, being the mass of whatever this curve we're integrating over. So maybe we've got some weird curve like this in 2-space, and you can think of this like a wire. And if we were to integrate over that entire curve, integrate over the wire of the density function, we would get the total mass of the wire. So the way that we go and compute this, this integral is first we go and parameterize the curve. So this could be a 2-dimensional or a 3-dimensional or higher integral. And what we'll do here is the first step is we'll parameterize c. That typically means we're going to find some vector valued function r of t that traces the curve. Now that we have the r of t, remember that r is just the same thing as the vector x, y, z. So we'll be able to pick out x, y, and z from our parameterization. And ds, this is actually the element of arc length. So if you recall, this was dx dt squared plus dy dt squared plus dz dt squared with respect to t. So once we parameterize the curve, that lets us get rid of the x, the y, the z, and the ds. And now will turn it into an integral over an interval of this function f of t dt. Maybe I shouldn't use the same letter f because our function is doubtless different. F of t dt. And then we integrate this using regular one-dimensional calculus. So we turn this integral over a curve back into an integral over something familiar, integral over an interval. Let's maybe look at some examples of this. So the first example is, this is where f of x, y, z is 1. And this just gives us the familiar definition of arc length. So if we're looking at the integral over some curve of ds, this gives us the length of that curve. And we've seen examples of this previous in the class. Let's maybe look at some that are a little meatier. Let's say we've got, we're integrating over a curve to be determined in a second of, say, x squared plus y squared ds, where c is the upper unit semicircle centered at the origin. So, well, what does this mean as far as evaluating this integral? First up, we're going to parameterize c. So c is this upper unit semicircle. If we go to sketch that out, that means as we are tracing out this circle right here, this is our path of integration. We're integrating over this path. If we go and parameterize this now, r of t, well, we can write this as cosine t sine t, which means our x takes on the value cosine t, y takes on the value sine t. ds, well, this is the square root of dx dt squared. Well, the derivative of x is negative sine t, plus dy dt squared. We take the derivative of y and we get cosine. And then this is all followed by dt. And what are the limits of integration here? Well, our circle is starting out at this far right hand corner at t equals 0. We trace out this half circle that's going to end at t equals pi, because remember, t is our angle here on the circle. That means we can rewrite this integral as the integral from 0 to pi. We now have actual concrete numbers for our limits of integration. X squared is cosine squared t. Y squared is sine squared t. ds, well, this ds right here, we can actually simplify this because this is sine squared plus cosine squared. So ds is dt, and we get the integral from 0 to pi. And again, sine squared plus cosine squared is 1. So we've got t from 0 to pi, which gives us pi. So that's the value of this this line integral or path integral. Now, how do you interpret this? What does this mean? Well, for this specific integral right here, we can think of this like a density function. So maybe we have this this piece of coil along here, and we want to know what the total mass of the coil is. We have its density at any given point, so the total mass of that coil is pi grams or pounds or whatever our unit is. Let's maybe look at another example. So let's now look at an example of the scalar line integral. Not the scalar, the vector line integral, excuse me. This is also sometimes called the field line integral. So the way this is defined is again the integral over some curve c of, now the function that we're integrating is actually a vector field. So you can think of this, the field of x, y, and z dotted with this dr right here that we'll define in just a second. And before we get into this, what does this mean? Well, if we think of this maybe like a force, and this is the direction of the path, this gives us force times direction, or force times distance, if you want to think of it that way. And we've seen that force dotted with distance gives us work. So you can think of this quantity right here like an infinitesimal amount of work done over part of this curve. So you can think of this integral as the total work done by the force acting on a particle that's constrained to move along a path. So let's look at maybe an example of how you would do this. So let's look at the integral over some path of, now our vector field, let's let this be xy and x squared dot dr, where c, this is the path, this is the line moving from the point 1, 0 to the point 0, 1. So again, if we were to sketch this path out, this starts out at the point 1, 0 and moves in the direction ending at point 0, 1. So first thing we'll do, like before, is we'll parameterize this curve. So r, or r of t. Now the way we parameterize lines, the sort of quick way to do this is we take t times the endpoint plus 1 minus t times the starting point. This is that convex combination. So this gives us t times the endpoint, 0, 1, plus 1 minus t times the starting point, 1, 0. And if we combine these together, we get 1 minus t, t. And this, when we make this convex combination, we rig it up so this is always going to be running on the interval 0 to 1. So what does that make x and y? Well, that says x is our first component, 1 minus t. It says y is the second component, t. And dr, well, dr, you can think of that like the derivative of r. We take the derivative, and we get negative 1, 1, dt. Now let's plug these in. So this gives us the integral from 0 to 1, those were our limits of integration from the interval, of xy. Well, xy will take these two functions, multiply them together, 1 minus t times t, followed by x squared, which is 1 minus t squared, dotted with dr, and dr we have is this vector, negative 1, 1 dt. And then we'll go through and algebraically simplify this. So when we dot these, we multiply the first components together. So 1 minus t times negative 1. This gives us t squared minus t. And then the second component, we multiply the y's together. 1 minus t squared times 1 is 1 minus t squared. So now we can simplify this a little bit more. This parenthetical statement right here is 1 minus 2t plus t squared. Then if we combine like terms here, we've got the integral from 0 to 1 of 2t squared. That was from our t squared components. And then next up we have the minus t minus 2t is minus 3t plus 1 dt. And now we'll integrate this term by term. So first up we've got t cubed over 3 minus 3t squared over 2 plus t evaluated from 0 to 1. We're going to plug in our limits of integration. First up at 0, everything zeroes out, so that we don't need to worry about that limit. Next we plug in t equals 1, and that gives us 2/3 minus 3/2 plus 1. And we go to simplify this out. This is 2/3 plus or minus 1/2, which gives us 1/6. So you can think of this again as the amount of work done on a particle constrained to move along this path, acting under this force field. So that's the idea of line integrals. We'll get a chance to see more of these in class.